I'm Alex Silkin. I'm a co-founder and CTO at Survios, and today I'll be talking about porting your VR game to the Oculus Quest in the context of Creed. So the key takeaways of this talk, I'm going to talk about some kind of common pitfalls that you'll probably fall into, like we did, some recommended workflows for getting that thing squeezed onto the Quest, and just some examples of the tricks we had to do to get it running on the Quest. And just a bit of an intro about the game. Are these videos playing? I'm not even. Are they actually playing? Okay. Sorry, I don't usually use Macs. So it's a boxing game. It's based on the Creed movie. It was originally launched in last fall on the PC and PlayStation platforms. It was our third Unreal Engine game. PlayStation was the lead SKU for this game. This is because you really want to have your most constrained platform as your lead SKU. We learned this the hard way with Raw Data, our first Unreal Engine title that came out on the PlayStation. PlayStation VR came out while Raw Data was in early access, so we weren't really planning to initially release it on the platform, and we just learned the hard way that trying to downport an experience is just really, really tough. So I know this talk is titled porting your title to the Quest, but I guess my first advice to you is don't do it. Just develop for the Quest from the beginning. And unfortunately, we had to do this again for Creed, but that's because the Oculus Quest came out almost a year after Creed came out. But it was such an amazing opportunity for us because we got to ship Creed as a launch title for the Quest, so we just couldn't pass it. But it was not easy. Okay, were the videos playing? Okay, I don't. All right, never mind. So you should really understand what you're developing for. So let's talk about what a Quest is and what's special about it, what's different about it than developing for a traditional console PC. So the Quest architecture is a little different than what you're probably used to. It has a tile-based render, also some called binning-based render. Essentially, PC and PSVR use immediate mode rendering. The entire screen is rendered together. But these mobile GPUs, what they do is they divide up the screen into tiles. The tiles are much smaller than what's demonstrated here on the screen. This is just for demonstrative purposes. And your draw calls are submitted as normal. You're not submitting them on a per tile basis. You're still submitting them normally for the entire screen. But when the GPU goes through and divides up the tiles, this is called the binning process. It takes all the triangles, it sorts them, and it figures out which tiles the triangles belong to. And then the GPU processes these tiles sequentially. So unlike once again, traditional graphics cards that you're probably used to, there's no VRAM, there's no dedicated RAM that the graphics card uses. It's actually a shared memory between CPU and GPU. This does mean that the GPU does not require as much memory because it's going through these small tiles, so it's much more efficient, so it's great for battery life, etc. But this is an important consideration for what things are just inefficient on this platform. So the rough target you should aim for is 300,000 verts for your entire scene, characters, etc. Creed shipped with around 200,000. You should aim for around 100 to 150 draw calls. Creed shipped with around 70. We were pretty aggressive with our environment optimization, merging a lot of things down to get those draw calls down. And something that you can't really change is Oculus Quest renders at 72 frames per second. That's the refresh rate of the screen. That is roughly equal to 13.8 milliseconds for a frame. This is the time you have for your GPU and your CPU, all the threads to do all the work for the frame and submit it to the system to render. And this is no negotiable, and you have to understand because the system is, it's like vertically sync, as with VSync. You're really locked to this refresh rate. So if you miss, like I like to call it like a train. If you miss this train, you have to wait for the next train. So you have to wait at the train station, waiting for the next train to arrive. So even if your frame took like 14 milliseconds or 15 milliseconds, you have to wait for the next time refresh rate. So essentially, if you keep missing that budget by even a little bit, Now you're essentially, each one of your frames is actually taking like 27 milliseconds. So you're just halving your frame rate. So you're essentially now your game is only running at 36 FPS, which is pretty vomit-inducing in VR. So you have to be really careful and strict about these budgets. So the tools in the debug environment, you have OVR metrics tool. That's pretty useful for a heads-up display that gives you some stats, particularly FPS. So if you're running a shipping build, you don't have a lot of your tools available. This is a nice handy way to just get some data when you're validating one of those final shipping builds. Render doc is really vital. It will it will really let you inspect what is happening in your scene. So if you're using Unreal, using a material editor, like a graphical editor for materials, it's a graphical tool. You connect some nodes together, and then that outputs some shader code. Well, you don't really know what it's outputting unless you really look at it, and sometimes the results can surprise you, and they can be less than efficient. You can also look at your draw call costs. So you have to be really mindful of the fact that, unlike the normal, traditional architectures, your draw calls are impacted by this GPU binning process, because your draw calls don't immediately go and render. They have to go through this binning process, which means all your draw call costs are a little grow a little bit, but you do get a relative cost of your draw calls to understand what's expensive, because not all draw calls are equal. You have a budget of 100, 150, but some draw calls are more expensive than other draw calls. So it's just a rough target. Snapdragon is good for just seeing how your threads are lined up, so you can see if you have scheduling issues, if you're stalling on things. Then you have Android Studio. So we really, even with PlayStation, we really try to develop as much as possible on the PC. The iteration time is so much faster. You just click play and you're there. With a Quest, you have to deploy to the target platform. It's a long process. But every once in a while, you do have to debug on the target platform. So most of the time, you're running gameplay code. If there's a bug in your gameplay code, it's not really platform specific. But every once in a while, there's something that shows up. So we advocate to use Android Studio over Visual Studio, because with Visual Studio, we saw that sometimes even stepping a line of code could take like 20 seconds. It was just way slower. And on the topic of using PC to iterate, so I'm sorry if everything's kind of Unreal context, because we're Unreal developers. Some of these things is still applicable to other engines, but with Unreal, you can basically launch the engine with these console parameters that essentially emulate the hardware rendering capabilities of the Quest, or at least the rendering hardware interface, so that you get a more accurate representation of how the scene will look on your PC. Of course, it's not as good, once again, as testing on a target platform, but really try to use as many tools as possible to test on the PC rather than the Quest, which might sound counterintuitive, but yeah. So we finally got the thing to compile and deploy on the device, and very disappointingly, the things just crashed on startup. So that's not fun, right? So what's going on with us? So we're running out of memory. So most likely it's going to happen to you too if you're developing for a much more powerful platform with a lot of memory. You're most likely going to start running out of memory. That's your first obstacle that you have to jump over. So Quest only has 2.75 gigabytes of RAM for your application. So that's pretty small in comparison to desktops that have 16 gigabytes of RAM nowadays easily. So on Unreal, you can use a console command memory port full. That will just give you a nice memory port of everything that's loaded in your scene, all the textures, etc., static meshes, assets, game object actor instances. And for us, textures were easily the thing that was blowing us way past the budget. So as a quick hack, we just globally clamped all the textures to a really small size just to let us launch the game on the device, just to start playing around with it. I mean, you can just clamp it to 32 by 32. Everything will look like Doom from the 90s, but at least it'll launch. And definitely use ASTC compression. So this will shrink your texture sizes, which is great, obviously, for, once again, managing the RAM applications. But it's also great for perf, because now the GPU doesn't have to load you're constrained by the bandwidth, essentially loading the textures in the GPU. So small textures will mean your GPU can do its work faster. So after we got a mem report, we found that a lot of our assets were loaded that we didn't even need to. This was the result of us being kind of sloppy because we could get away with it in PlayStation VR and we weren't quite hitting that memory limit. So in Unreal, there's a console command that essentially allows you to get the reference paths to any asset. So we essentially did a dive through, found textures that were questionable, like why is this UI texture loaded in the middle of the game that's normally from the main menu, things of that nature. So for us, this has actually been still, to this day, often a issue. UMG/UI is the usual culprit of a lot of stuff being loaded that shouldn't be loaded. A lot of different UMG widgets. UMG is the framework for UI in Unreal, just referencing a bunch of things that it shouldn't reference, referencing characters or referencing from different game mode, etc. So, and UI textures also do not stream. So that's an additional kind of gotcha in Unreal. So that really increases the problem. And then we had a lot of unnecessary hard references to assets. So for example, we'll have like a data table for a system that refers to, say, character assets or audio for some system for every single map or for every single character. Well, in Creed, you're only ever in one ring and you're only ever fighting one character. So it's instead of having those be as hard references, there should really be soft references. So dynamically loading them, and somewhat Unreal specific, but just in general, you should try to avoid blueprint dependencies. Blueprints are, essentially the archetypes, templates of an actor that is spawned, or like a prefab if you use Unity. So sometimes people don't realize that casting a blueprint class to another class is a hard reference because you essentially need to access its functions and properties, etc. So it's better to use an interface potentially to break that up if you want to make a blueprint interface, or just even move the reference function or variable to C++ so you can just cast to a C++ base class, because accessing the C++ class doesn't require you to load the blueprint class reference. Anyway, so let's move on to optimization time. So allegedly, this is where the fun begins. So let's find the bottleneck. With optimization, you should really do it in a data-driven manner. Figure out what's actually costing you your wasting your cycles, and target that. And this is kind of potentially not a very scientific approach of trial and error. So in Unreal, there's a stat unit command. It's pretty standard to like get a frame timing and see how much your threads are taking. But it's a little useless because, as I mentioned, you're basically locked to 72 frames per second. So your frame time is always going to be like 14 milliseconds or whatever. And then your game thread is potentially going to be waiting on the draw thread to catch up. So really you want to be trying to isolate what it is that's causing you to go over the budget. So the trial and error here is, if you think it's the CPU thread, just pause and unpause the game. That will just pause all your gameplay logic. And if your frame rate suddenly stabilizes, then that's your bottleneck. If you think it's your fill rate, so it's fill rate being the cost of shading every single pixel, well, just decrease the screen resolution to like 10%. And if suddenly your frame rate stabilizes, then that's your bottleneck. Shaders in Unreal is a show materials console command, which essentially just turns off all the shaders. Everything's just shaded with like a standard gray shader. And draw calls, there's console commands to toggle specific objects, like show static meshes, show skeleton meshes. Once again, if you just hide all your static meshes and your frame rate stabilizes, that's the thing that's bringing you over your budget. So once you kind of start isolating your general bottleneck, that's when you want to start drilling into the stats. So Unreal has a pretty complex stat system, essentially. And you type in stat space and the stat group name. So stat RHI, stat scene rendering. Those are standard. Those are some good examples of stats that give you an idea what's going on. Stat RHI, for example, will tell you how many draw calls you're doing, like how much memory you have loaded for your GPU. Stat scene rendering lets you further drill into like what's your render thread doing. So you might see that. Shadow or culling is taking a really long time. So one thing you have to keep in mind is that this stat system is really complex in Unreal, but which means it also really affects perf. It distorts the numbers it reports. I don't remember like the numbers on the Quest, but just on PlayStation, just turning on any one of these stats just suddenly adds 2 milliseconds to your CPU, which can easily just kick you over the your budget. So now all of a sudden you're waiting for an extra frame, your stats get distorted. So that's kind of useless. And on the other hand, kind of hilariously, the stat rendering is using this really antiquated UI rendering system called Canvas. So most of Unreal now uses Slate. And those, like, each character is like adding like a draw color or something. So then once again, you use this system and it's just distorting your numbers. So as a kind of quick workaround, of course, it's better to use RenderDoc if you really want to have a deep dive through. But it's convenient to be able to just have a glance at your stats, so you can have QA running through all your maps and kind of record any bottlenecks, any hot areas. We created a lightweight Slate widget that has some stats that we decided that are kind of useful that we show there. It's rendered using Slate, so it doesn't impact performance, and it's composed on the screen using this debug draw service. It shows the average and max values, so that's useful because, like, I caught our world tick time. Just the average was good, but the tick time was like 10 milliseconds higher. And I realized, like, just from there, then I did a profile, and I realized, like, every few milliseconds we had something taking 10 milliseconds. So we had these spikes causing irregular frame rate. And we have INI defining the budget for text color coding. So green is good, yellow is probably danger zone, red is definitely bad. So that's convenient as well because we define different budgets for different platforms if you have different frame rate or et cetera. So there's some existing cached engine values that are already there. So we can already read them ourselves. We also modified the engine for some additional values, specifically world tick time, because like I said, the game thread time that's reported by stat unit is kind of useless because that's affected by waiting on the rendering thread, et cetera. Most of the time, we're really interested in what your world tick time is, which is where all your gameplay logic is. That's the thing you're going to be optimizing most of the time. So CPU in Unreal, it's pretty standard. We stat star file, stat star file it's a console command. Use session front end. So starting in 4.23, Unreal Insights is coming. It's a whole new profiler. It's way more powerful. It also does profiling for memory loading, etc. So that's going to make your life way easier. But it's really standard across really PlayStation, etc. What we found is moving components is usually one of the most expensive things. Especially if you have like these really deep attachment hierarchies. So the simplest is just detach your hidden and disabled scene components, like audio components, effects components. Especially if you have like designers working with you, sometimes they can be pretty sloppy and they attach all these things that aren't even being used right now, and it's just costing you cycles. I know it sounds kind of mundane, but honestly, when you're on a really constrained platform, you really can't get away with just being sloppy like that. All right, that's a typo. I don't know. It says overlays. That's supposed to say overlaps. My bad. So overlaps. So it's when you detect that one trigger box is within another trigger box. So those are really expensive in Unreal. Every time you move a component, then they update the overlaps. On top of that, it's kind of sloppy the way they wrote them is, even if you don't have a single component in the attachment chain that updates an overlap, it will still go through this entire like update overlap chain down the children. So once again, if you have a long attachment chain, it will go through that. So as a optimization, we just kind of deleted that because we didn't even want to use them. And that saved us a lot of cycles since we weren't even using overlaps. We actually, starting in raw data, we wrote our own async overlap system that updates overlaps on a worker thread. And that doesn't block your thread every time you move an object. Obviously, it's deferred, but we use events for when overlaps happen anyway. So that's been a huge kind of optimization for us. I know it's easy to like say, hey, my hand is close to this bottle. I'm just going to stick like one trigger box in the hand, one trigger box in the bottle. You can't be sloppy like that on these platforms, especially once you start having thousands of bottles and two hands and touching everything. So ticking, once again, very simple. Just disable tick when not needed. So often designers just have components and actors just tick when they're not even, they just have a flag to disable certain behavior, but they're still ticking. So tick interval is another thing. often if the things are not significant, they don't even need to tick every frame. Once something you have to watch out for is, in Unreal at least, the tick interval. You can they added tick intervals, so you can say like, okay, this tick ticks like once every like 0.1 seconds or something, but there's no control over which frame you tick. So now if you have a frame rate hike or whatever, now all of a sudden things just get pushed into one frame. So you have like one frame where a bunch of things tick, the next frame nothing ticks. So you really want to load balance. So we've modified the engine once again to really help us load balance and tick things, one frame versus the other frame. I mean, the easiest is just to say, okay, like half the enemies tick in this frame, half the enemies tick in the other frame. Now all of a sudden, technically, you just did a 50% optimization. Good job. Blueprint logic, it's really slow. Try not to have any blueprint logic in tick. Try to nativize as much as possible. Throw it in C++ if you can. Active pooling, just spawning things dynamically is pretty damn expensive. So we developed our own active pooling system, which automatically disables like physics collision and a bunch of other things, so we don't have to do it manually every time. If you're using UMG UI, you can't get away without using validation boxes. Let's move on to the draw calls. Make sure to use multi-view. So multi-view allows you to do one draw call per eye. Makes no sense not to use it unless you really want to double your draw calls for some reason. Try to merge your geometry as much as possible. You can do it in Maya, or Unreal has a merge actors feature. We actually modified Unreal to like make an unmerge actors feature that we serialize like the previous state. It's great for iteration, but make sure when you merge things, you actually minimize the material count, because even if you merge a whole bunch of actors together, but they're all using different materials still, that's still each individual draw call per material. So now you actually just made things worse, to be honest, because now things don't call. So minimize your material count. Instance as much as you can. If you like instant static meshes, then it's just one draw call. That's even better. And like I said, not all draw calls are equal. Some draw calls are more expensive. Switching materials is expensive. Switching meshes is even more expensive. And actually, the complexity of the mesh actually affects the draw call cost. This is a capture of render doc of part of the scene in Creed. This is actually a stadium piece. You can see how we merged this one stadium piece all the way from the floor to the ceiling. We divided the stadium between 5 to 7 pieces, and we used 3 shared texture atlases. In this one capture, you can see the only 2 textures that are attached to this draw call is essentially the diffuse map and the shadow map. So we used 3 texture atlases across the entire stadium. So moving on to GPU, disable early Z-Pass. That's an optimization in Unreal. So early Z-Pass is actually redundant in the tile-based renderer. So the binning process actually pre-sorts all the triangles so that it avoids overdraw by only rendering the triangle that's closest to the screen. So the Z-Pass in Unreal actually counteracts that. Also, don't use alpha test. So if you have like a texture that tells the pixel like this is transparent or not, actually don't use that. I know that's like a common optimization, but that actually counteracts once again this early sorting that happens on the hardware level in the GPU, because the GPU already pre-sorts all the triangles. So this actually forces it to invalidate that whole calculation. So get rid of specular. Specular added about 100 instructions for us per pixel. I know that's like an entire hard pill to swallow because things are usually shiny in the world. But for us, the environment took up most of the screen, and just removing that specular just gave us 2 milliseconds back on the GPU. So that was pretty massive gains. We still kept it on the characters because you're boxing, the characters are sweaty. We wanted to simulate that shininess of their sweat. And post-processing. So that's an even tougher pill to swallow because post-processing just is such an easy way to just really drastically change the appearance of the entire scene. The problem is it really does not play well with the architecture of the Quest, because with post-processing, essentially you have to do a whole new render pass. You have to take the rendered image and you have to pull it back into the binning process and operate on that again. So it's really expensive. Something we're talking about in the future is just modifying our shaders for just a global shader effects, so that you can potentially apply things on a per object basis. So it's not a screen space effect, but simulate those things. And also stay away from dynamic lights. Bake as much as you can. It's kind of obvious, I guess. But we actually faked lighting on a per shader, per object basis where we needed. So, speaking of about faking post-processing and bluing and dynamic lights. So, I don't know. Is that video playing? It's not. Sorry. Okay, so probably should have tested this, but essentially it's a ring. There's spotlights floating around, and the spotlights hit the ring, and you can actually see a circle. So for the bloom around the spotlights, instead of using post-processing bloom, just attach a sprite, way cheaper. And for the actual circle on the ground, what we did is we actually projected, instead of using a dynamic light to calculate, how the spotlight affects it, we just projected a circular patterns on the floor there, and that's way cheaper. It only added about 20 instructions, but we didn't want to add the thing is that's 20 instructions for every single pixel. So we didn't want that active during the actual fight because the spotlights were only floating around the flight. During this intro sequence, and then during the fight, we would have particle systems and all these other things spawning and using up more draw calls. So we put it in a kind of global if statement to disable that. One thing you have to watch out for if you're using Unreal is if statements in the material graph still actually evaluate both conditions, and then they choose which one. So this is something we picked up in RenderDoc. So instead, we wrote this just in the USF file. We wrote the actual shader code with the if statement in there, and we called that using a custom node. In Unreal, you can use a custom node to call into any shader code by name. So mentioned texture atlases. Make sure to combine all your textures as much as possible. Like I said, switching between textures is a pretty expensive draw call operation. So you want to batch things as much as possible. So we used about 2-3 for each environment. Make sure you use ASTC compression. So you can use RenderDoc to confirm that, or memory port to confirm that your textures were actually successfully converted to ASTC. Sometimes textures failed because of some weird things that the artist did. Similarly, actually, speaking about texture dimensions, make sure they're power of 2. Just make sure your textures are clean, because if they're not power of 2, then they won't mip map properly, and they're not going to stream properly. And mip mapping is great for caching too, because then it's not going to use the highest res texture when it doesn't need to, when it's far away. And on the topic of dependent versus independent texture reads, so dependent here refers to you using one texture's, you're looking up in one texture and using that result to actually look into another texture. So we found that the cost here was actually about the same. So if you can then potentially bake some expensive calculation you're doing at GPU at runtime, just bake that into a texture and use that to look up into another texture. MSA, it's actually cheaper on tile-based renders. So, and honestly, in VR, you really should be using that. We ship with 4x MSA. Shader hitches was another issue we had. Basically, anytime a particle spawned for the first time in the game, you would get a hitch. So in Unreal, there's a console command r.save shader cache, which basically we had to run through the entire game, make as thoroughly as possible, use this console command, outputs a binary file with all the shader permutations, and then you can package with that. In 421, they have this PSO caching feature, which I hear is making that easier. We had to ship in 420. Fixed foveated rendering, if you don't know what that is essentially rendering the screen at different resolutions depending on if it's the center of the image or it's the edges of the image. If it's in your peripheral, it doesn't need to be as high res. So you can actually control the resolutions of those regions. I mean, worst case scenario, you might even have to down res even the center image if you're really fill rate bound. And try to avoid long thin triangles, because those can really not play nice with the whole binning process, because then the bounding box, I'm still not, reading online, I'm still confused whether they have dealt with this or not, but essentially, as far as I understand, the bounding box can make the long thin strips fall into multiple tiles where they're not even really contributing any pixels, and you're just making all those tiles more expensive. Memory, I'll talk about the fact that it's shared bandwidth. So that does mean that if you're doing some expensive stuff on the CPU with the memory, it can actually affect the GPU and vice versa. which once again is useful to like be able to toggle one of the processes on and off to figure out which one's actually causing the bottlenecks. Some memory stomp tracking is so essentially if you have somewhere writing or reading into memory that it doesn't actually own, some deallocated memory blocks, or Unreal has a memory stomp allocator that you can compile with, but we found out that it caused the game to crash really, really fast because it really pads all the memory. So like I said, ideally you test on the PC, but we had this case where our game was crashing like 5 times a day randomly in like random regions. So we knew it was a memory stomp, and it was only happening on the on the Quest build. So it's a pretty kind of nasty situation. So we found out that you can use essentially the built-in Android memory stomp allocator here, and we caught this stomp happening deep inside of the OVR compositor, specifically related to the splash page. So essentially in their like load screen pop push functionality, they were accidentally writing over some memory that they didn't own. So we helped them fix that crash in their system. Yeah, so other general tips, they, just like PlayStation VR, there's some TRCs related to how fast, the game loads, how long you spend before you show the load screen. So what we've been doing basically for our titles is we usually load into an empty room first. And then because if you have, if you're trying to load into your regular map first, it will try to load that, and you just will not be able to push the load screen fast enough. The game will just be stalling. But even there, there's often issues with just global assets being referenced, like global managers referencing some assets with hard references where they're not needed, etc. So you're going to need to break those reference chains if you want to have a quick load time. Audio, the default Android audio does not actually spatialize audio. At least it didn't when we shipped. And so you can use Android Audio Mixer Android or other third-party plugins for spatialization. It actually messed up all our mixing, and we had to ship. So unfortunately, we shipped without spatialization because it was either the audio team was going to somehow, I don't know, try to redo all our audio for the entire game or not ship. So yeah, so that's about it from all the tips. Does anyone have any questions? Sorry, that was pretty, I don't know if you guys were ready for such a technical deep dive or whatever. I don't know. Hopefully that was useful to people who are thinking about targeting the Quest. Yeah.
Hey, that was really interesting and useful because I am in the same boat of thinking about porting. But I have a more general question on, like, once you've done it and you've got it working on the Quest, and but you primarily develop on PC, like, how do you keep your integration working and keep, because it's such a pain, like trying to test it again and again and again. I'm curious, so how do you manage that, making sure your developers continue to keep it working once you've done the original ports?
Yeah, well, that's why I don't like the word port. It's more parallel development, right? So you choose your target SKU, and you have ideally QA that hammer on this build every day. You have continuous integration, so Jenkins or something that basically outputs these builds on a daily or hourly basis, and then daily basis, depending on if it's a full package or whatever. And you have QA actually testing these things on a regular basis so that they can catch issues really as fast as possible. So it's definitely a lot of process, and I'm not saying it's perfect. Like it's a constant battle of like you getting in fights with other people because they break things. So, yeah.
Hi, thank you.
Yeah.
First off, are your slides going to be available? Do you know? Is
that? Yeah, I can upload them. Yeah.
Okay. And when you were mentioning some console commands, except for the few that were ADB, was that the Unreal console you're talking about?
Yeah, it's all in the Unreal. So yeah.
All right. Thank you.
Yeah.
Hi. I was wondering, for people starting to develop a new experience, would you recommend that they start by developing it on Rift and then port to Quest, or start on Quest and then add more stuff to take advantage of the higher performance on Rift?
Well, like you would always be kind of developing alongside, because all your testing is probably most of your iteration is going to be on PC. But if you're going to try to launch in the Quest, like I said, avoid porting. Try to launch that thing on the Quest as soon as possible, so you can at least periodically see that when you add things, you didn't just blow yourself way past the budget. Because now you added 20 things, and they're all past the budget. Now you have to determine like what needs to be cut and what doesn't. So it's always easier to add things than remove things. You know,
Okay.
removing things is killing your babies. Adding things is making more babies, I guess.
That's interesting. I hear a lot of people say the opposite, actually.
What do
You
you mean?
should just focus on developing the experience first without worrying about performance, and then kind of do that after the fact.
It's, I guess I don't know, a question of philosophy.
All right. Thank you.
Yeah.
Hi there, thanks. That was really interesting. Can you tell us anything at all or comment at all about the submission process and how quickly they're turning approvals and communication at all?
I don't know if I can really give an accurate estimation of that, because I'm on the software side really, so I'm not part of the schmoozing process.
Okay, fair enough.
Yeah.
Okay.